Hello students, last class we have seen about resistors in series and resistors in parallel. So I hope you all are clear with that. Today in this class we will see about heating effect of electric current. So what is heating effect of electric current? So you all have come across with this. For example, if you have seen in your room, if you keep the mobile for charging, after 1 or 2 hours, if you touch the mobile without its back cover, you will feel a sense of heat there. Even if your television is used for so much time, you can see if there is a stabilizer is there, you can see that the stabilizer is heated. Or if you use even TV also, sometimes it is heated. So what is there? Why it is getting heated? Why if you use your laptop or mobile, so for many or maximum time, why you feel the heat? This is because of heating effect of electric current. So what is heating effect of electric current? See, as we should know that in the circuit there must be energy is given by this battery. Energy is given by this battery in the circuit. Okay. So where this energy is going? Some part of the energy is used to maintain the electric current in the circuit. So to maintain the electric current, some part of the energy must be used. Okay. So to maintain electric current, some part of the energy is used. So remaining energy, where it is going? The electrical energy produced by this where it is going. Okay. So some part of energy is used by maintaining the electric current. And if the circuit is having other energies like fan and all, the some part of energy is converted to mechanical energy. But most of the times what happens when the circuit is purely resistive, okay, purely resistive circuits, it does not have any inductors or capacitors. So when the purely resistive circuit is there, that time most of the energy is dissipated. Complete energy is continually dissipated in the form of heat. That is, if the electrical circuit is purely resistive, or you could say in the purely in the purely resistive electrical circuit, resistive electrical circuit, the energy is continually or continuously, you can say, dissipated in the form of heat, in the form of heat. This is called as this is called as heating effect of electric current. This is called as heating effect of electric current. Heating effect of electric current. So where it is used? It is used in electric iron, next electric coils, electric heating coils. So examples of heating effect of electric currents are electric iron and electric heating coils. So it is very much easy. So purely resistive circuit means maximum energy gets dissipated. So you can see in the mobile there is not that much of heat that produced by the iron. So if the iron box it is taking too much of heat, whereas mobile is not taking that much of it. Why? Because in the mobile circuit is not purely resistive. Only some part of the energy is being dissipated in the form of heat. But when it comes to electric iron, it is purely resistive, and so that complete electrical energy is dissipated in the form of heat. And same with the electric heating coils. Okay, so there we are using this, the heating effect of electric current. So come once again, what is the heating effect of electric current? In the purely resistive electrical circuit, in the purely resistive electrical circuit, the energy is continually dissipated in the form of heat. This is called as heating effect of electric current. Examples: electric iron or electric heating coils. So then, in another one thing you should remember, we know the formula R is equal to rho into L by A. For the heating effect of electric current, or for the brightness, for the heat energy to be released more, the resistance must have to be more. You should remember this. When there is much resistance, then we can say that there is maximum heat energy is released. Heat energy releases because the kinetic energy of the molecules releases and they go and bombard each other. That means electrons starts bombarding each other. That means the resistance has to be made more. When the resistance has to be more, we have to keep rho more, L more and A less. I hope you are understanding. These are directly connected, these are inversely connected. This one is. For resistance to be more, resistivity has to be more. Electrical resistivity has to be more. Length of the conductor should be more. But area of cross section, that is thickness, should be less. So this is why if you can use electric heating coil, if you say electric heating coil, the length should be more. That is why the electric heating coil are coiled like this. So that the length should come more. Here the length is more. The total length is more, but thickness is less. And usually we use alloy here because we want the resistivity to be more. We want this resistivity to be more. If you see the electrical resistivity table, first comes metals, next comes alloys, lastly non-metals or conductors, alloys and insulators. We cannot use insulators. Insulators may be having higher resistivity values, but we cannot use them because they cannot flow. They cannot allow the current to flow. Then what is the use? We have to use either metals or alloys. But when you see that electrical resistivity table, alloys are having more resistivity compared to metals. See, nichrome is having more resistivity. Manganese is having more resistivity compared to copper, silver, aluminum. So that is why usually these kind of coils, electrical heater coils, are made up of alloys, nichrome. Why they are made up of alloys? Just because the electrical resistivity has to be more. To conduct the electric current or to produce maximum heat energy, the electrical resistivity has to be more. Hence, we found that the electrical resistivity of alloy is more compared to electrical resistivity of metals. Hence, the alloys are used in making what we can say electric heating coils. Okay, and length should be more. That is why they are circled like that. They are coiled more, such that they should get maximum length of the coil, and thickness should be less. Usually the thickness will be less. So this thing you have to remember. And what is heating effect of electric current? In the purely resistive electrical circuit, the energy is continually dissipated in the form of heat. This is known as heating effect of. This is called as heating effect of electric current. You can use it in your electrical irons. You can use it in your electrical heating coils. I hope you all are aware with this. In your electrical heating coils, you have seen, already seen. If I have already seen both the electrical heating coils and electrical iron. In that, what is happening? All the electrical energy, because of the purely resistive circuit, all the electrical energy is getting dissipated in the form of heat. So there you are getting maximum heat energy. So this is called as heating effect of electric current. So we'll see some formula of heating effect of electric current. What would be the formulas we will see here? See, what is happening in heating effect of electric current? Energy is being used in the form of heat. So let us consider it as electrical energy is getting converted into heat energy. So I will take the formulas H as heat energy. I will take the formula H as heat energy. So what is here happening here is the circuit. If you see, if I draw the circuit, you can see, okay. If I take resistive here, so now we okay plus minus. So here the current is flowing. In the circuit, what happening? Charges are flowing, right? In time t, time is t, I is equal to q by t. Charges are flowing in time t, and V is the potential difference. V is the potential difference. So electrical energy is nothing but whatever the work done is. Okay? Whatever the work done is given by that electrical energy. So how we can say H is equal to C VQ by T VQ by T, isn't it? If you see, H is equal to VQ by T, but Q by T is what? I is equal to Q by T. So H is equal to VI T. See, here we want, this is with into time T. This is in 1 second. H is equal to VQ by T in 1 second. If I make it for 5 seconds, 6 seconds, then into T will come. So that we can say H is equal to VIT. So H is equal to VIT is one formula. You remember this first formula of electron heat energy. In place of V, I will put Ohm's law. V is equal to what? IR into IT. Right? I into I square R into T. This is the second formula of which one? Heat energy. So in place of V, I can put other thing. What? V is equal to IR. So what will be my I? If I remove this, move this side, I is equal to my V by R. Getting point? So H is equal to I square R T, V I T. So V in place of I will put V by R into T. So H is equal to what? V into V square into T by R. This is the third formula. So these are the three important formulas of heat energy or electrical energy. You should remember all these formulas. Or another one, Vi is equal to some, we call it as power. Vi is equal to power. We'll see in the next class. Vi is equal to power. Okay, then I can say that H is equal to P into T. I can say that P into T. Power is rate of doing work. Okay, that is P into T. I can say that is heat energy. So you should remember all these three formulas. H equal to Vi into T. Don't need to remember this. Only remember this. Whichever I put the box. H is equal to Vi into T. H is equal to I square RT. H is equal to V square T by R. These three formulas are important. Or at least you remember any one of the formula. Other things you can convert by putting V equal to IR or I equal to V by R. Okay. If the current is not given in the circuit, use this formula. Current should not be given in the circuit. Okay. That means potential difference, resistance and time are given and no current is given. Use this. If potential difference is not given, current, resistance, time is given, use this. Okay. If resistance itself is not given, then use this. So we can use this formula. If instead of voltage and current, power is given, then we can use this formula. Okay, we can see about that in our numerical section. But 90% of the time, maximum we use either this or this formula. Okay, rather than those formulas, we use this formula or that formula. So H equal to I square RT and H equal to V square T by R. You should remember this. Okay, H is here directly proportional to R. That means whatever the heat energy is there, that is your depends on your resistive circuit. If it is purely resistive, that means more resistance is there, then you can have the maximum heating effect. So pi nichrome is used, pi alloy is used in making electrical heater coils, because the resistivity of alloys are more compared to the resistivity of conductor. Hence alloys are used in making the electrical electrical heater coils. Okay, this is regarding heating effect of electric current. You should remember these formulas. H equal to I square RT, H equal to V square T by R. Then H equal to V into T, H equal to V Q by T. Okay, you should remember all these formulas. And heating effect of electric current. Let me define what is heating effect of electric current. Heating effect of electric current is nothing but in the purely resistive electrical circuit. In the purely resistive electrical circuit, the electrical energy is dissipated or continually dissipated in the form of heat. This process or this is called as heating effect of electric current. Why it happens? Because the energy has to be used. Energy cannot be converted or cannot be destroyed or cannot be created, but it can be transferred, it has to be used. So whatever the energy given by this battery has to be used, and some part of the energy is used to maintain the current, and some part of the energy is used to maintain other works like mechanical works. That is, if it is fan, rotating the fan and all those things. And if it is purely resistive circuit, 99% of the energy, completely maximum energy, is getting dissipated in the form of heat. So that is heating effect of electric current, where we find that electric heater coils and electrical irons. Okay, there the maximum heat is getting generated. So there we call it as, there we can see heating effect of electric current. And after that we can see these formulas. H is equal to E Q by T into T. So for T times, current is flowing with potential difference, with V as the potential difference. So VQ by T into T. So Q by T is what? My current. H is equal to VIT. Okay. So in place of V I can put IR. IR into IT. IR into I into T. So H is equal to I means I into I will become I square. R I kept as it is, T is here. So H is equal to I square R T. So another formula is, in place of I, here in place of I will put V by R, because V is equal to IR is my Ohm's law. I will keep it I here only. If I take R this side, I is equal to V by R, it becomes R is other side with multiplication. If I take it in the left hand side, it will become division, right? So V is equal to IR means, if I keep only I here, this is multiplication with I. If it comes, it becomes division with V. So V by R. So that V by R, I put it in the place of I. So V into V by R into T. So V into V becomes V square. V square into T, V square T divided by R. So this is, see, if nothing is there means here multiplication is there. You have to understand that. That's a basic concept. If nothing is there means multiplication is there. V square into T is nothing but V square T. Here also V equal to IR nothing but I into R. I square RT nothing but I square into R into T. So I hope you all know all these things. V is potential difference. H is what? Electrical heat energy. That means heat energy here. Okay. Energy is expressed in the form of, what is the SI unit of energy? You have to remember the SI unit of energy is Joule. Whichever energy it may be. Maybe it is electrical energy, mechanical energy, potential energy, kinetic energy, heat energy. Whichever energy is there, the SI unit of energy is joules. Okay, heat energy is expressed SI unit joule, potential difference SI unit volt, Q is charge SI unit coulomb, time SI unit second. This is also time. Here also same, but I came here SI unit of I, current, amperes. Don't forget that. H is equal to same thing. Resistance, opposition according to the flow of current. What is the SI unit? Ohm. Don't forget that. Ohm is the SI unit. And other electrical resistivity SI unit. What is the SI unit of electrical resistivity? Ohm meter. So we can say that ohm meter like this. So regarding this we understood. Any doubts you can ask me. Okay. So this is regarding heating effect of electric current. So what is heating effect of electric current? Let me tell you once again. What we have discussed today is heating effect of electric current definition and their examples, and why alloys are used to make the electrical heater coils by the formula R equal to rho into L by A. We understood that, that is electrical resistivity has to be more. If the more heat energy is to be dissipated, then there must be high resistance. If there must be high resistance, then there must be electrical resistivity more. So the electrical resistivity of alloys are more compared to the electrical resistivity of conductor. Hence alloys are used to make electrical heater coils rather than conductors. Okay, and after that you have to use these three formulas, very much important formulas. Those are H is equal to, I am going to write those three formulas directly. H is equal to V into I into T, or you can say VIT. If I replace I with V by R and V equal to IR, my second formula again by replacing V equal to IR. So if I put IR, what it will become? IR IT means I square RT. This is my second formula. It is already told. So final answer will always come in joules, because heat energy is expressed in joules. H equal to I square RT. My third formula is H equal to, see, if I put I equal to V by R, if I put V by R into V into T, V into V, V square T by R. So H equal to V square T by R. So if I take VI as power, it will come next. If I take it as power, H is equal to T into T. So these three are very, very important formula. This one we can see it later. So you have to remember all these three formulas: heating effect of electric currents, examples, and where we find heating effect of electric current. Okay, and why SI units of all electrical resistivity, resistance, and why alloys are used in making the electrical heater coils. And remember, heating effect of electric current is purely high in purely resistive circuit. It is high in the purely resistive circuit. Understood? So this process is called as heating effect of electric current. So remember all these things. What is heating effect of electric current? In the purely resistive electrical circuit, the electrical energy is continually dissipated in the form of heat. This process is called as heating effect of electric current, where it is used in electrical heater coils and electrical iron machines. There we are using the heating effect of electric current. In others also there is some very less part of heating effect is there. Okay, if you take mobile, there will be some heat is dissipated. If you take computer and if you use it more time due to the electrical energy, so there will be little bit of heat dissipation. But when it comes in the large wave, we take purely resistive circuit and maximum heat energy gets dissipated. That is, electrical energies get dissipated in the form of heat. So this is called heating effect of electric current. So formulas: H equal to, H is heat energy, VIT, H equal to I square RT, H equal to V square T by V square RT. Sorry, the third one, V square T R by R. Sorry, this is not R here. We should not get R. So if I put I is equal to V by R, then V square T by R. So H equal to V square T by R and H is equal to T into T. These are the formulas. So remaining things we will see in the next class.